Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's our pleasure to have Nishant Chandran speaking today. So Nishant is from UCLA, and he's a student of Amit Sahai and Rafal Oshevsky, and he's going to be speaking about a new and interesting paradigm for cryptography.
Thanks very much, Seni. Okay, so just some references in case you're interested. This appears in Crypto this year. There's also a full version that I'll give you the link to later. It's joint work with Vipul Goyal, Ryan Moriarty, and Rafi Ostrovsky. Okay, so typically in cryptography, every party has some sort of an identity. So for example, it could be your public key given through some public key infrastructure. It could be your biometric that identifies you in the network, or for example, in the case of identity-based encryption, it could be your email ID. So if someone knows your public key, then they can encrypt a message and send it to you. Or if someone knows your email address, they can encrypt a message to you such that only you can decrypt the message. Right? So the question is, can we have any other different kinds of identities? What else can we use as an identity? So the question we ask over here is, how about where you are? Right? In other words, three-dimensional Euclidean coordinates. Can we use this in order to do cryptography? I mean, the fact that I'm standing at this particular place gives me some sort of an identity. I'm here at this particular point of time, so that gives me some identity. So can we use cryptography, I mean, out of this kind of notion? First, where might something like this be useful? Let's consider a situation where you have a military base in the United States that wants to communicate with the military base in Iraq. Right? So in a traditional crypto setting, the military bases would share a secret key, exchange it between themselves, and then they can exchange messages back and forth, and everything is good. Right? But then what happens? You have, say, an honest officer who's captured by the terrorists, and then he's tortured, and he finally reveals the secret key. Right? So ideally, what would we like to have? Maybe we trust physical security more. Right? So maybe we are able to guarantee somehow through some physical means that those who are inside a particular geographical region are good. So maybe we can guarantee that geographically, if someone has entered the military base in Iraq, then he's a good guy. Right? So we want to be able to send a message to anyone who is geographically present inside this military base in Iraq. So ideally, we want to send a message encrypted to the military base in Iraq, and only someone who's at a particular geographical position, someone who possesses maybe some XYZ coordinates, can decrypt the message, and no one else can decrypt this message. One can think of other applications as well. You can have position-based authentication. So for example, if you want to receive a message from this military base in Iraq, and you want to have the guarantee that this message actually physically originated from the military base in Iraq. Some other examples could be position-based access control. So for example, if I want to authorize someone to be able to use a printer which is inside a room, but then if he goes a little far away, then he no longer has access to print in this location. And you can think of many more such examples. So the problem informally is as follows. Say we have a set of verifiers who are present at various geographical positions in space. And we have a prover who's present at some geographical position P. To become clear why I use the terms verifier and prover shortly. And the goal is to exchange a key with the prover if and only if the prover is in fact at position P. So the verifiers want to talk to this prover, and if and only if the prover is at this position P, which has some coordinates x, y, z, then a key must be exchanged with the prover. Otherwise, nothing should happen. Now, before we look at that task, let's look at a corresponding related task, which is called secure positioning, which is a bit more basic. again we have a set of verifiers who wish to now simply verify the position claim of a prover at position P. So there is a prover again at position P, and now we are not interested in a key exchange, but simply the prover says, hey, I'm at XYZ, and the verifiers want to verify that in fact the prover is at XYZ and he's not lying. And the verifiers can run an interactive protocol with the prover at P in order to verify this claim. So this problem has actually been studied in a bunch of works in wireless security, but there is an inherent problem with all of them, so we'll get to that in a bit. So what is the previous technique that has been used for secure positioning? First, the assumption is that all messages travel at the speed of light. Radio waves achieve this, GPSs use this in their current operation. We actually don't require that they travel at a speed of light, but we just require that we can transmit messages as fast as an adversary can, that's all. So if an adversary can transmit something at some particular speed, then even we can do so at that particular speed. That's the only thing we need over here. But it's convenient to just say speed of light. So now we have a verifier and a prover, right? And they can use a time of response. So how do they do this? So the verifier sends the random nonce R to the prover, and the prover responds back with this random nonce. Right? And the verifier measures how long it takes for this whole protocol to take place. Right? And then just based on distance and the speed at which it travels, if the prover is responding back, you get sort of an estimate of the distance. What is the advantage of the protocol? The advantage is that the prover cannot claim to be closer to the verifier than he actually is. Right? So he can be very close by and claim to be extremely far away. That's possible. Right? He can just simply delay his response such that it's coming from far away. But if he is in fact far away, he cannot claim to be very close by. So one can think about generalizing this, and in fact that's what Kapkun and Hubo did in 2005, and use triangulation. So basically you have three verifiers, V1, V2, and V3, and say you have a prover P. So now each of these verifiers send out random nonces R1, R2, and R3 to the prover at P, right? And the prover has to respond back with the random nonce to each of the verifiers. Right? Again, the three verifiers measure the time of response and verify the position claim. And you can just show just by triangulation that this is secure. Right? It's secure, but it assumes a single adversary. Right? What is the problem? Suppose you have a position P, and you did have multiple colluding provers. Right? In fact, there is an attack. What is the attack? Say you have three provers over here, P1, P2, and P3, such that P1 is close to V1, P2 is close to V2, and so on. Right? So now when V1 sends out the response R1, P1 is closer to V1 than P is. So P1 can respond back in time. And that's the same case with all the other adversarial provers as well. So they can forge their responses as if it's coming from a single prover at position P. So rest of the talk outline is going to be as follows. I'll first describe our model, basic model, in a little bit more detail. We call it the vanilla model. It's just basically the model that I was talking so far and a bit more formalization. Then we'll talk about the problem of secure positioning. I'll first show that the attack that I just described can be generalized in a way, and in fact secure positioning is impossible in the vanilla model, even if you allow any sort of computational assumptions. So any crypto assumptions that you may be willing to make, it's impossible in the vanilla model. Right? So given that we have a strong impossibility result, the question is, can we do position-based cryptography in any other model? And it turns out that the bounded retrieval model, which was a model that's been in use quite a lot recently, I'll talk about it in detail, that gives rise to positive information theoretic results.
Would the model preclude one beacon sending out, or one verifier sending out a message to a prover that has to then send it to three provers?
Sure. Our impossibility result just rules out that as well.
Okay, because that might be a viable way of doing
our impossibility result, you can make any assumption like that. That also it rules out.
Okay.
It takes into account that the prover could get information from multiple verifiers and have to send it to multiple verifiers as well, and even then it's there is an explicit attack that adversaries can carry out.
But I think that might get around the multiple prover example you had before, because the provers would have to communicate between each other in order to send a response out.
Sure, but there is a way that they can do it, and I'll just get to that. Yeah. And then after that, we'll get to what we really started off with. What we wanted to do, position-based key exchange. So can we actually exchange a key with this particular prover at position P? And again, we present positive information theoretic results in the boundary retrieval model. So first, an outline of the vanilla model. So you have multiple verifiers, how many ever, V1, V2, V3 in this diagram. You have a prover P. For now, let's just assume P lies inside the convex hull. There are ways we can avoid that in some cases. We'll assume that the verifiers can send messages at any point of time to the prover with the speed of light. Next, we'll assume that verifiers can record the time at which they send the messages, the time at which they receive the messages, and so on. We'll assume that verifiers share a secret channel between themselves that they can use to communicate before the protocol, during the protocol, after the protocol. So, yeah. And finally, we'll assume that we have multiple coordinating adversaries. And since we are showing a lower bound, we'll even assume that they are computationally bounded. And even if they are computationally bounded, our lower bound holds. Yeah.
You assume that the verifiers have synchronized clocks too, right?
Yes. Yes.
Just to understand.
Yeah. So the first theorem that we show is that there does not exist any protocol to achieve secure positioning in the vanilla model. And as a direct corollary of this, we get that position-based key exchange is also impossible in the vanilla model. I mean, any protocol for position-based key exchange is also can be easily seen to be a protocol for secure positioning also. So I'll just present a high-level sketch of our lower bound. Say we have verifiers V1, V2, V3, V4, and we have a position P. And now we have multiple colluding provers, P1, P2, P3, P4. And we're going to now describe we're going to describe the attack in the following way. We're going to say, let there be any protocol that achieves it for a prover at position P, and we'll show how these provers, adversarial provers P1, P2, P3, and P4 can simulate exactly the same thing, exactly as if there were someone at position P responding to the verifiers. So it's a generalization of the attack that I presented earlier. So basically, any PI can run an exact copy of the prover. That's what we're going to show. And PI is going to respond to VI. So P3 will respond to V3, P1 will respond to V1, and so on. But all the PIs will basically run exactly the same copy as the prover. We'll show that. Basically, what happens is that PJ can, so any prover at position P will be getting information from, say, V3 and V2, and say he has to respond back to V1, right? So does the total time taken for something like this is the time taken for a message to travel from V3 to P, because P has to make use of that information in the first place, and then it has to go to V1, right? But then the adversary, so in other words, the blue path is the path taken if there were to be an honest prover over here at position P, right? But then an adversary always has a shortcut like this. And you can basically show through some triangle inequalities that this is always possible, right? And no matter from where it comes, if it comes from here also, the same thing can be done. So it can be shown that PI can simulate an exactly the same copy as P, maybe at a slightly later instance of time, but then since PI is closer to VI than position P, he can respond back in time, and we are done. Okay. So the implication of the lower bound is that secure positioning and hence position-based cryptography is impossible in the vanilla model, and even with computational assumptions. Note, in the lower bound, we never made use of any sort of computation. I mean, if whatever the prover was doing, the same thing the adversaries can do as well, and there's no sort of, it doesn't rely on any computational assumption also. So the question is, other alternate models where we can do position-based cryptography. And it turns out we can, and here are some of the constructions and proofs. The bounded retrieval model is an extension of the bounded storage model that was introduced by Maurer in '92. What does the model say? It says that it assumes that there exists a long string X, which is of, say, length n, and it has some high min entropy. And it's either generated by some party or it just comes up in the sky. I mean, the original bounded storage model said that X just comes up in the sky, and assume that there is this string out there in the sky that has some high min entropy that every party can see. Furthermore, it assumes that all parties, including honest parties, have some retrieval bound beta n for some 0 less than beta less than 1. Right? So in other words, the adversaries can look at the entire X, right, and store any arbitrary function of this X, but then the amount that they can retrieve is bounded, and it cannot be, it's only some constant fraction of the total length of the string. And a bunch of works have studied this model in great detail, but I won't get into all of them, but we'll just talk about how this fits into our setting. So what do we mean by the BRM in the context of position-based cryptography? So again, we have V1, V2, and V3. We have multiple colluding provers. And it's like the vanilla model, except now since we're going to present information theoretic results, we do not even assume that the adversaries are computationally bounded. So they can run in exponential time, for example, the adversaries. So we assume that the verifiers can broadcast some huge X, which is some large string X that has some high min entropy. And adversaries and provers, honest provers as well, can store only a small f of x as x passes by. So they have some retrieval bounds. They cannot download the whole x as it passes by. And a restriction of the BRM and the BSM is that adversaries cannot reflect x. In other words, they cannot send x back and forth, and this just violates the BSM as well as BRM framework. So to make things a little bit more clear, some assumptions we make is that we assume first that computation is instantaneous. Modern GPSs do perform some computation while using this kind of speed of light kind of assumption. We can relax it, but then we'll get a slight error in the position. We may not be able to say that a person is at x, y, z, but maybe only be able to say that he's within some particular region if we start allowing error. We also assume that x travels in its entirety and not as a stream. Again, we can relax this, but then again we'll get a small error in the region that we are secure positioning. So the question is, how can one physically realize BRM? Is it possible? We have some thoughts on it. It seems reasonable that an adversary can only retrieve some small amount of information as a string passes by. We're assuming that this is a huge burst of information that's coming by. It seems reasonable that he can look at it, but then he has time only to look at some parts of it and only store a small fraction of it. Another way they could do it is the verifiers could split X into different parts and broadcast it on separate frequencies. And maybe it's hard for an adversary to listen in on all frequencies simultaneously, but then can listen only into certain frequencies and gets only part of the information. Okay. So now going to our constructions, what are some of the primitives that we need? We require these tools called locally computable pseudorandom generators from the works of Salil Vadan. What are they basically? PRG takes as input a string X with high min entropy, just like what I was saying, this large string X with high min entropy. And it takes a very short seed K, which is chosen from a uniformly random distribution. And the output of the PRG of x comma k, is guaranteed to be statistically close to uniform, even given the seed k and some a of x for arbitrary bounded output length function a. Okay, and the most important thing over here for us is that it's locally computable. So what do I mean by locally computable? In order to compute PRG of x comma k, one doesn't need to look at the entire stream. The locally computable PRG from Salil Vadan basically uses the sample and extract paradigm. So basically it says that if I have the stream x, then all I need to do is look at few bits of this x randomly selected, some bits of it, and then I can apply the extractor, and I will get something that's statistically close to uniform. So it's good for us because honest parties also are not allowed to look at the, they cannot download the whole thing. They can just look like a little bit of it and compute some fraction. Okay. So as a warm-up, let's just first present secure positioning in one-dimensional space. It's an easy thing to do for now. So we have V1 and V2, who are two verifiers on a straight line, right? And now we have a position P that's on the straight line, and we simply wish to verify that a prover is at position P. So how can they do this? V1 and V2 pre-share a short seed K, which is a seed to this PRG. V1 is going to sample this X, which comes from this distribution, this long string which has high min entropy. And X and K are going to be broadcast such that they reach this position P exactly at the same time. Okay. What does a prover at position P do? Computes PRG of x comma k and responds to the V1 with PRG of x comma k. Okay. Again, V1 measures time of response and accepts the response is correct and if it were received at the right time. Okay. Now just quickly, the correctness of the protocol is quite easy to see. So note that a prover at P can compute PRG of x comma k. He gets both x and k, so he can compute PRG of x comma k. V1 can compute PRG of x comma k when broadcasting x. When broadcasting x, V1 already knows key k, so he can compute PRG of x comma k and therefore can verify the response correctly. And the response of the prover from P will be on time because x and k are sent such that they arrive at P at the same time, so it's just the total round trip time from V1. That's it. Now, why is this a secure positioning protocol? I'll just give you some proof intuition for this. So note that there are two kinds of adversaries over here. Broadly, you can look at them as two classes of adversaries. Adversaries who are between V1 and P, call them P1. Right? And adversaries who are between P and V2, call them P2. Now, when these two streams travel past, what do each of these adversaries get to see? P1 can store some a of x, right, for some arbitrary function a. Right? P2 can store k. Right? And then these streams still travel and P1 gets to see k afterwards, P2 gets to see x afterwards. So what can P1 do? P1 can respond to V1 in time. He can respond. He's much closer to V1 than P is, so he can respond in time. But then he has only a of x and k. Right? He got to see x first, so he could compute some a of x. Right? And then he got to see k. So he just got a of x and k. Right? So by the property of pseudorandom generators, this is statistically close to uniform. So he cannot guess the response better than just guessing at random. So P1 is okay. What about P2? P2 can compute PRG of x comma k because he gets to see k first, right? And then he gets to see x, so he can compute PRG of x comma k. But then he is farther away from V1 than P is. Right? So just by the distance bounding for him to respond back in time is going to take longer than someone over here. So he's not going to be able to respond back in time. Okay? So this does our secure positioning protocol in one-dimensional space. We can sort of generalize this in three-dimensional space. How do we do this? For now, I'll just make an unreasonable assumption and then we'll show how to get rid of it. So again, you have V1, V2, V3, V4. You have a prover at position P. Now V1 is going to pick K1, which is the short seed to this PRG, and pre-share it with all the other verifiers. V2 is going to sample X1, V3 is going to sample X2, V4 is going to sample X3. Basically, each of them sample a particular X. And for now, let's make the assumption that Vi can store all the X's. So assume for now that V3 can store the X2, V2 can store the X1, and V4 can store X3. We'll show how to get rid of it in a minute. So now they can all broadcast their respective streams such that they reach position P at the same time. And the prover does an iterative application of the PRG. So he takes K1 and X1, PRG of X1 comma K1 to get K2, PRG of X2 comma K2 to get K3, and PRG of X3 comma K3 to get K4. And K4 is broadcast to all 4 verifiers. Okay. Again, verifiers check response and time of response. Now, the security of this protocol will follow from the security of position-based key exchange that I'll present a bit later. But for now, let's just look at the correctness of the protocol. Right. So this is what each of the verifiers began with, and then they require a prover at position P to be able to compute K4. Right. But in order to verify that the response K4, the verifiers themselves need to be able to compute K4. Right. How do they compute K4? So actually it turns out the verifiers cannot compute K4 if they don't store the XIs. Right. Why is that the case? So remember, the KIs were applied iteratively, right? And in order to compute K4, I needed K3. In order to compute K3, I needed K2, and so on, right? So V3 might need K2 before broadcasting X2 in order to compute K3, because if he broadcasts X2, then there's no way for him to compute K3 if he doesn't know K2 at that particular point of time, and nobody else can as well. Right? But it just might be the case that V3 might have to broadcast X2 before or same time as V2 broadcasts X1. So at this point, even K2 is not even fixed. So no one knows the value of K2, but at that time V3 might have already had to broadcast X2. Right? So it seems that the verifiers might not be able to compute K4 themselves. So how do we get around this? So we get around this as follows. We basically let V1, V2, V3, and V4 pick K1, K2, K3, K4 at random before the protocol. Basically fix every key that goes into each application of the PRG. Now clearly verifiers know K4 because they picked it themselves, but they must help the prover compute it. So as before, V1 broadcasts K1, V2 broadcasts X1, and in addition broadcasts PRG of X1 comma K1 exclusive OR with K2. So in other words, what they are doing is fixing the keys K1, K2, K3, K4, right? Making one of the shares be from the iteration. So when you apply PRG of X1 comma K1, you'll get one of the shares, right? And the other share is broadcast. So sort of just a secret sharing of the keys. And the other verifiers do a similar kind of thing. And verifiers basically secret share the KIs and broadcast one share. And you can show that coupled with the security of the regular protocol and secret sharing, that this protocol is also secure. So protocol is basically V1 broadcasts K1, V2 broadcasts X1 and K2 prime, which is a share, V3 broadcasts X2 and K3 prime, and so on. And how does the prover compute it? Prover computes PRG of X1 comma K1. That gives basically a share to the next key. Exclusive that with K2 prime gives the share that's to be used, gives K2 itself, right? Then computes PRG of X2 comma K2 and goes forth in the process. So the bottom line in secure positioning is that we can do secure positioning in 3-dimensional in the boundary retrieval model. And even if there is a small variance in delivery time or in measurement of the times at which you are getting the message, that can be tolerated, but you'll get a small positioning error. So the question is, what else can we do in this model? Can the whole power of this can be realized only if we can actually get some sort of a key exchange with a prover at position P. So in fact, we can do that. Let's look at again information theoretic key exchange in 1-dimensional space. So as a reminder, the secure positioning protocol, we had V1 and V2 along a straight line, and you had a position P. Right? There were two types of adversaries, P1 and P2, and we noted that P1 could not compute the key. Right? If you viewed the response as a key, it was already statistically close to uniform, so great, it has the property of the key. Right? Furthermore, we noted that P1 could not compute the key, so it seems like halfway we are done. P2 could compute the key but could not respond in time. That was the problem that we had. So this cannot be directly used for key exchange because there exists an adversary over here who can compute the key. but we seem to have already taken care of half the problem, right? So maybe we can repeat it in the other direction and couple it in some way and get key exchange. So in fact, that's what we do. So V1 picks K1 and secret shares it with V2, sends it to V2 as well. V1 also samples X2. V2 samples this long string X1. And they both send such that they arrive at P at the same time. And you do PRG of X1 comma K1 to get K2, and then PRG of X2 comma K2 to get K3. So again, you have two types of adversarial provers, P1 and P2. P1 could store A of X2 comma K1, and you can give him K1 for free. And P2 can store A of X1 comma K1. So it seems like no adversary gets to learn K2 before or at the same time that he sees X2. That's the only way he can compute PRG of X2 comma K2. So in fact, that is true, and this is in fact a secure key exchange protocol in one-dimensional space. In order to get a key exchange protocol in three-dimensional space, we generalize it the same way that we did a generalization of the positioning. Again, for now, assume the verifiers can store the x's. V1 will broadcast K1 and X4, V2 will broadcast X1 and X5, two streams, V3 will broadcast X2, V4 will broadcast X3. Do a iterative application of the PRG, and K6 is the final key. Okay. Now, some of the subtleties that arise in the proof is that there could be multiple colluding provers everywhere in space. You could have one guy over here computing A of X4 comma K1, then sending across to this guy who computes A of X3, combines it in some way, sends it across to P4, and so on. And it could be endless, because we are looking at key exchange. We are looking at there's no restriction on when he has to respond back. He could work on it for forever later on, and so on. We want information theoretic security. So it seems like there are some of these issues over here that creep up. So the proof idea is as follows. It works in two parts. We first have a geometric argument. We first need a lemma ruling out any adversary simultaneously receiving all messages of the verifier. So we know that the prover does receive all messages from the verifier simultaneously. How do we know that there doesn't exist some other point in space where all messages of the verifier do reach there simultaneously? This in fact characterizes regions within the convex hull where position-based key exchange is possible. For sample region where this might look at if the endpoints are the verifiers, then the red region shows where all we can get position-based key exchange. We can show that the region is very large. And then we need to combine the geometric arguments to actually characterize information that adversaries at different positions get. What information does each adversary learn, and what can he send across to someone else? Finally, we need to put that all together, and that's where the extractor arguments come. We build on techniques from recent work of intrusion-resilient random secret sharing of Zumbowski and Petrzak. And we show a reduction of the security of our protocol to a slight generalization of TP07 that allow multiple adversaries working in parallel. So just a reminder about intrusion-resilient random secret sharing scheme, IRRSS in short. Basically, you have n parties, S1, S2, Sn, right? And they have long streams, X1, X2, X3, and Xn. Right? K1 is chosen at random and given to S1. And S1 computes PRG of X1, comma K1, gets K2, sends it to S2, who computes PRG of X2, comma K2, gets K3, sends it to S3, and so on. Right? Basically, this iterative application of the PRG. And Sn outputs the key Kn plus 1. Okay? Now, what can an adversary do over here? This models something like a virus that can get into these processors, learn a little bit of information, and get out. Right? So basically, an adversary can corrupt any sequence of players. So an adversary can go to S3, learn a little bit of information, then go to S5, learn a little bit of more information, get back to S3, learn some more information, and so on. Right? So a boundary adversary can corrupt a sequence of players with repetition as long as the sequence is valid. What do I mean by valid over here? The valid sequence must not contain the exact reconstruction sequence as a subsequence. So over here, the way to reconstruct PRG, the way to reconstruct Kn plus 1 would be to do S1, S2, S3, and so on up to Sn. If you were able to look at S1, S2, and so on, and then go all the way to Sn in that order, then you can learn Kn plus 1 simply by doing whatever the honest parties would do, right? So as long as the valid sequence does not contain S1 to Sn as a subsequence, then they guarantee that Kn plus 1 is statistically close to uniform, right? So over here in this example, the first sequence is invalid because it contains 1, 2, 3, 4, 5 as a subsequence, but the second sequence is valid because it does not contain 1, 2, 3, 4, 5 as a subsequence. So Dembowski and Petrzak show that Kn plus 1 is statistically close to uniform as long as you prohibit adversaries from corrupting exactly via this reconstruction sequence. So at a high level, the reduction to IRRSS would be as follows. We can model again S1, S2, S3, S4, S5 having different xi's. We can give all adversaries K1 for free. And then basically, for any adversary in our scheme over here, any adversary who computes any sort of information, right, we can construct a corresponding adversary in their scheme that has a valid corruption sequence. Right? So we can translate anybody in our scheme, any adversary in our scheme, to an adversary in their scheme that has some sort of valid corruption sequence. Right? So we'll call that adversary as a corresponding adversary. So an adversary that we have in our scheme translates to a corresponding adversary in their scheme with some valid corruption sequence. But this was just one single adversary. So we need to make sure that if you have multiple adversaries, how do you combine them in order to represent their views, right? So we need a theorem to show that you can combine two adversaries that have valid corruption sequences in order to get a single adversary that has again a valid corruption sequence and so on. And we need to show that this is possible for any adversary in our setting. And there we need to make use of geometric lemmas. So to conclude, some other results that we have shown in the paper is to get position-based key exchange in the boundary retrieval model for the entire convex hull region, not just the red region that I was talking about. But for that, we need to make use of some computational assumptions as well. We also show how you can extend our techniques to get a protocol for position-based public key infrastructure. So if I want to develop a public key infrastructure just based on position, then we can do that. If I want to do some sort of a position-based multi-party computation where my input should be based on the position, and that needs to come with some trust guarantee that, yeah, indeed I am at this particular position, and I can give my input into the multi-party computation. Some open questions remain. Are there other models where we can do position-based key exchange? I mean, we got the boundary retrieval model. Computational assumption doesn't help too much, except for this particular thing, it doesn't help. Are there any other models in joint work with Serge Fur, Vipul Goyal, and Rafi Ostrovsky? We have some initial results in the quantum model where we can show that even without making any assumption on bounded storage or anything like that, just regular quantum model, we can get position-based cryptography. Finally, could there be any other applications of position-based cryptography? Thanks a lot, and the full version of the paper is available on ePrint. Thanks. Yeah.
How does this interact with, say, revocation? How do you revoke a position?
Well, it's sort of the position is tied to the time. So sort of the verifiers broadcast something, and they know at that particular time, this is the key that would have resulted in the protocol, right? And if they want to do a protocol again, if they want to send a message to somebody else at that position at a later instance of time, they need to run the whole thing again.
Everything is revoked automatically.
Everything's revoked automatically because key is tied to the time.
I guess I have another question, which is, you show your impossibility result in the plain model with basically no setup at all. If you get some very small setup, some way to get something more.
So any kind of So unless you assume that you have tamper-proof hardware that cannot be cloned, then any sort of setup also doesn't help. We show that as well, but we require this strong assumption that, so if it's possible for all parties who ever want their position to be verified or anything like that, to meet with the verifiers beforehand at some point of time, and the verifiers give them some trusted hardware that cannot be tampered with, then you can do position-based key exchange. We didn't find that interesting because we don't want everyone to come to the verifiers in the first place. I mean, the idea is to use only position as sort of an identity. But any other kind of setup assumption, any kind of keys, anything, that none of them work. We can show that. Yeah.
If 300 people are moving the airplane, do the positions get confused?
You mean the provers are moving, or?
Well, yeah, so they're all passengers crossing the Atlantic somewhere.
If you want to verify their positions, well, if they are in motion, yeah, I guess you can do it by sort of a repeated application of the protocol. So measure their position at some particular point of time, then measure their position again, and then you can make sure that they're following some sort of. I mean, we thought about this in terms of satellites. You can sort of make sure that they are following their orbit by sort of measuring their positions at different points of time. And that would be.
Air travelers and satellites go still quite a bit slower than this.
Yeah, quite a bit slower. So. In fact, actually, there is some work that talks about the following two cases. So our impossibility result directly does not prevent the following two. If verifiers were moving, or if verifiers were hidden, so if the adversaries did not know the positions of the verifiers. Although this impossibility result directly doesn't hold true, we have attacks on both those protocols that exist. And in fact, we do believe that most of our work does extend into a general impossibility result for those models as well. So I really don't know of any other model where the impossibility result doesn't go through, other than, say, boundary retrieval model and the quantum model. So it's, yeah.
Another question. So, did you consider sort of the flip side of the problem, which would sort of maybe say that your impossibility result is actually a positive result in terms of like privacy? So, what if I want to hide my location, right? So maybe I have my iPhone, like, or something, or some device, and it can be triangulated by the software towers. And but I might not want that to happen. So, or even sort of a more, going to your military base application, right? Maybe I'm a soldier or somewhere, and I want to be triangulated by enemies who can actually ping me for some reason. So you see the problem of sort of how you provide privacy in that setting, right? So what do I need to do in order to make sure that my position can be pinpointed to a certain degree of accuracy?
Even though I'm responding back to all these verifiers.
Yeah, so in terms of, okay, so maybe it's a situation, so if you think of like a plane, for example, right? So I don't know exactly how radar works, but I'm assuming, you sort of send a signal that bounces off the plane somehow, right? And then so maybe something like that, where you don't have a choice. You can basically be pinged.
Oh, okay, you can basically be pinged, but then...
What can you do in order to protect yourself, right? Or maybe if you have multiple planes, now can these sets of multiple planes figure out a way so that they can not be sort of
well,
pinpointed exactly?
If the verifiers can make sure that there are these colluding provers don't exist, then you cannot guarantee anything. I mean, you would require, if I as a verifier need to be confused as to where this guy is, right? Then I need to use what we have, I need to believe that there are adversarial, or by design there are provers also who will be giving these responses, right? So I don't know as is if any of this can be used, but yeah, maybe something might be over there of interest. Thanks.